Hey, Professor Foreman, I'm Linji here again, and this time I'm catching up the last problem that I did it incorrectly. Okay, let's start. So the problem is still 1.1.11, which is an is a sequence such that n is greater or equal to 1, and 2 minus an times an plus 1 equal to 1, and what happens to an when n goes to infinity. And the part that I didn't prove, which is the limit exists, and I also need to prove it is bounded and monotonic. So the first what I'm gonna do is change the original equation, which is 2 minus an and an plus 1 equal to 1 to an plus 1 is actually equal to 1 over 2 minus an. Okay, and I also need an plus 1 minus an, which will be 1 over 2 an minus an, and we multiply 2 minus an to each side, 2 an, which gives me 1 minus 2 minus an times an, and 2 minus an, which gives me 1 minus 2an minus an squared over 2 minus an, which is equal to 1 minus 2an plus an squared 2 minus an, which is equal to an minus 1 squared over 2 minus an, because this is an squared minus 2an plus 1, which converts to this. Okay, and let's see the limits. So if 0 is less than an and an is less than 1, then we can have 1 is actually less than 2 minus an, and is 1 is smaller than 2 minus an, and is smaller than 2 minus an is smaller to 2, because we can see here, if an is less than 1, if an is between 0 and 1, then 2 minus an is definitely gonna be between 1 and 2, right? And so an plus 1 is actually gonna be greater than 1/2 and less than 1, because we can we can see here, if an is between 0 and 1, then we can prove this condition. So once the sequence gets into the I just gonna write it down. So once the sequence gets into the interval 0, 1, it's gonna stay there. But an plus 1 minus an, which is the equation here, equal to an minus 1 squared 2 minus an. And when an is between 0 and 1, or I should say 2 minus an is between 1 and 2. This equation must be greater than 0 because a squared is always greater or equal to 0, and when it's between underneath here is between 1 or 2, this equation must be always positive, which means the an plus 1 minus an will always be positive. And so once the sequence gets into the interval 0 and 1, it is monotonic increasing and bounded. Because when an plus 1 minus an is always greater, that means an is always smaller than an plus 1, and always smaller than an plus 2, and always smaller than 1, right? Okay, and we can also show some special cases, like when an is less than 0, then an plus 1 will still be between 0 and 1, because we can bring it here. It's still gonna, for example, when an is negative 1, then an plus 1, let's say a1 is negative 1, then a2 must gonna be 1 over 2 minus negative 1, which is 1/3. It's still between 0 and 1, right? And similarly, when an is greater than 2, that implies an plus 1 is less than 0 if an equal to an plus 1 is less than 0, because when an equal to 2, when an equal to 2, n plus 1 is gonna be less than 0, right? And if an equal to 1, then that's one gonna be interesting is an plus 1, which is a2, right? Gonna be 1 over 2 minus 1. It's still 1. So which means when an equal to 1, an plus 1 is still 1, no matter what n equals to what. Okay, so that should prove that the limit exists and it is bounded at a monotonic. So then we can continue to the equation I had before, which is when the limit n goes to infinity and an equal to L, and limited when n goes to infinity, an plus 1 is gonna still be L, which we bring the L's to the equation, which is 2 minus L, and L equals to 1. And by solving that, we get 2L minus L squared equal to 1, and L squared minus 2L plus 1 equal to 0, and L is 1. And that proves when the n goes to infinity, an goes to 1. Okay, hope that works. Thank you.